In this section, we're going to talk about ions and electrolytes really quickly by reviewing what ionic compounds are and what their formulas indicate about the structures, and then what happens to these solutions when they are dissolved and dissociate into electrolytes. Instead of talking about dipole a lot, we're going to spend most of our time this semester talking about electrolytes and ion dipole forces. Now, these are another way of saying ionic complexes, and these really give people trouble, especially if it's been a while since they took 151. So if you need to, I would go back and look at ionic complexes in Chapter 4, electrolytes in 8.5, and ion dipole forces in Chapter 11, and look back over that material again. I do have some packets online too you can look over to practice. Nonetheless, right, ion dipole force comes from the attraction between the ionic charge on the ions in these salts and the dipole in the water molecule. So the positive side of the water molecule is attracted to the negative anion. The negative side of that water molecule is attracted to the positive cation. And as a result, they circle these ions and dissolve them in solution. So NaCl is called a strong electrolyte because it dissociates, which means to split 100%. So any ion that completely dissociates in water is considered a strong electrolyte. On the other hand, a weak electrolyte is usually a molecular complex that dissociates only partially. So whereas NaCl gives 100% ions, HCN is going to give about 1% ions. 99% of it will stay in the initial molecular form. We are going to talk about chemicals like HCN in the second half of the semester, so we'll get to that a little bit later. For now, we want to talk about ionic complexes almost completely. If you remember back to 151, we have this picture of predictable ions that form based on their position on the periodic table. And again, this was all based on the idea of the octet rule. Every element wants to get to 8 valence electrons. So fluorine, of course, has 7, so it wants to get 1 more. Oxygen has 6 valence electrons, it wants to get 2 more. Again, remember that electrons are negatively charged. Nitrogen has 5 valence electrons, so it needs to get 3 more. These in the middle don't really form many ions. Some of these down here do, but we don't need to get into those right now. Group 1 has 1 valence electron. It likes to lose that negative charge to go back to the previous row. Magnesium has 2 valence electrons. It loses those 2 negative charges to get back to its octet. Aluminum is the only ion that always forms a +3. So again, it has 3 valence electrons being in row 3A. It loses those 3 valence electrons to go back to the octet of the previous row. Again, cations are always going to be metals, and they will always form positive ions. The nonmetals, on the other hand, always form negative ions. So we can tell what kind of ion these things will form just based on their position on the periodic table. Now, what we can say about salts is that these charges are always equal and opposite. If we have an NaCl salt, we're going to have a +1 and -1, so the formula is just NaCl. If we have MgCl2, this is going to be made up of 1 magnesium ion and 2 chloride ions, right? Because we need 2 negatives to be equal and opposite to the 2 positive. And we're going to do a lot of this looking at salts and breaking down what ions are in them to look at these electrolytes. So again, if this is something you're struggling with a bit, make sure you go back and review this. It's also, we could write magnesium this way, with 1 magnesium and 2 chlorides. The 2 in front is a coefficient. It still means we have 2 individual chloride ions. One of the things you can do here as well is to draw Cl2. That happens a lot, and I just want to point out that that is incorrect. Right? There is no such thing as a Cl2 ion. If I see that on a paper, it's automatically going to be wrong. So just kind of keep that in mind. We have sodium sulfide. Again, here we have, because they're both in group 1, this is 2 +1 ions, and a sulfur -2. Again, you can write that with coefficients here. You can also have AlCl3, 1 aluminum, 3 individual chloride ions, but you can also write it this way. In addition to the monoatomic ion, we also have the polyatomic ions. So we're going through this kind of quickly, but polyatomic ions are groups of atoms bonded together that have an overall positive or negative charge. Most of the ions we're going to see this semester are ions left over from General Chemistry 1, so you should already be familiar with these, but I don't make you memorize them. There's a few ions we are going to see all the time, and so it will be much easier for you if you just memorize them now. However, right, I will always give you a list of ions, and that will help you kind of figure out what you need to know as we work through them. But the ions we're going to use all the time are the nitrate ion, the acetate ion, the hydroxide ion, the carbonate ion, the sulfate ion, and the phosphate ion. Those are the ones we're going to see often, and if you are familiar with them and comfortable with them, it will make your life a lot easier. We're also going to use the bicarbonate ion in the lab a bunch. Just kitchen chemistry, bicarbonates are really easy chemical to use and to measure and to buy, so we will probably see that one quite a bit as well. So when salts have polyatomic ions, right, keep in mind that there's only one positive ion and one negative ion only. So if you look at a compound that has a bunch of elements in it, you probably have a polyatomic ion. The other thing to keep in mind about salts is that we always have a metal and a nonmetal. So sodium is a metal ion, nitrate is a nonmetal ion. So if you can recognize this is our metal, then it's just, oh, we have a nitrate here as well. Again, if you've memorized these ions, they're a lot easier to see. Just like before, though, they have to have equal amounts of positive and negative charge. So sodium nitrate is going to have one sodium ion, one nitrate ion. Positive, negative, equal amounts of charge. Again, the 3 on the bottom does not measure charge. That's just the number of oxygens we have. Okay, if we have a larger positive charge, we're going to need more negative charges. So barium nitrate has 2 nitrates, because each nitrate is -1, it counterbalances the barium plus 2. So take a second and figure out what the charges of these ions should be based on where they are on the periodic table, and then fit them together to figure out what the stable formula of the ionic compound should be. Go ahead and pause the video and then just hit play again when you're ready to see the answer. Okay, so lithium is in group 1, it should be +1. Oxygen is in group 6, so it should be -2. So we need 2 lithiums to have equal amounts of charge. So again, we write that with the subscript Li2O. The subscript implies this is all now part of the same compound. This would be called lithium oxide. Again, ionic compounds don't use prefixes. But we're not really going to do naming at all. You might see that as we go. But naming is not super important for this class. The other one has a calcium ion, that's a group 2, so it has to be +2. If we want to get equal amounts of positive and negative charge with the phosphate, it's a little challenging because 2 doesn't go into 3 and 3 doesn't go into 2, but they both go into 6. So to get equal amounts of positive and negative charge, 6+ and 6-, we're going to need 3 calcium ions and 2 phosphate ions to give us the formula Ca3 in brackets PO4, 2. Transition metals, this area in the D elements is where this gets tricky. Because these are not main group elements, they don't have to form the same charge all the time. So iron, for example, can be iron 2, which is iron +2, it can be iron 3, which is iron +3, or it can even be, in some limited cases, iron +4. Although usually that's a pretty reactive state. So we oftentimes have to figure out what the charge of the transition metal is based on what it's paired with. So if we say, oh, FeCl2, well, Fe is paired to 2 chlorides, therefore, in order for those charges to be equal, iron must be a +2. Again, FeO looks like a different form of iron, but because oxygen is -2 and they have to be equal, iron is still +2. Right? This one is commonly mistaken. People look at this and say, oh, iron +2. But actually, when you break it up, each sulfate is -2. So in fact, this would be an iron +4 ion. It needs 4 positives to balance out the 2 negative 2s in the 2 sulfate ions. So these are 3 salts. Again, we can tell because there is a metal in the first element of all 3. See if you can figure out which ions and charges are in each of these salts. What are the ions, how many of them exist, and the charges. Keep in mind that most of these 3 salts have polyatomic ions, and only the formula on the right with nickel has a transition metal. So we are going to have to figure out what that charge is based on its pairing. Again, pause the video, press play when you're ready to see the answer. So the first one, aluminum bromide. Each bromide is going to be -1, and there are 3 of them, so we're going to get 3 individual bromide ions. Again, they're not going to be connected anyway, but we have 3 of them. We also know aluminum is in group 3, so it always forms a +3 ion. The next is sodium sulfate. Sulfate is always an SO4 -2 ion. We're not going to split that into individual atoms because it is a stable polyatomic ion. We also have 2 sodiums, so each one is +1. Finally, we have nickel carbonate. Because it's a transitional metal, we don't know what that charge is, but because the carbonate is -2, the nickel has to be +2.